Hello everyone and welcome to the video for the start of chapter 6. This is 6.1 dealing with slope fields and Euler's method. The objectives for this video are 1. Use initial conditions to find a particular solution to a differential equation. Number 2, use slope fields to approximate solutions to differential equations. And the third one is to use Euler's method to approximate solutions to differential equations. Now, in terms of the AP exam, the 1 and 2 are going to be things that are topics that are covered. We're going to show you a little bit with Euler's method, but you're not going to be doing a ton with it. So it's just basically to see what that process is and be able to generate a couple of points. And we will also add in a program on your calculator that will help you do this as well. Let's start out with a couple of some definitions that you need to be familiar with in this chapter. The first one deals with what's called a differential equation, and I will abbreviate that DE instead of having to write that out every time. The differential equation is an equation that involves x, y, and the derivatives of y. So you could see in the problem, you could see a y prime, y double prime, you could see the fifth derivative, okay? All of those are possibilities, and you're going to be looking at these types of equations. Now, for our purposes, in terms of the problems you do, you're going to see various derivatives in these differential equations, but for the most part, what you're going to be working with is going to be things that are you're not going to see so much with the second derivative or third derivative. Most of it will be with just the first derivative in there. The order of a differential equation is the highest order derivative in that differential equation. For example, if you see a second derivative, that's a second order differential equation. The first order would be with first derivative. If you see a fourth derivative in there, if that's the highest one, then that would be a fourth order differential equation. A solution to a differential equation is some function y equals f of x that will satisfy that differential equation when y and its derivatives are replaced by f of x and its derivatives. So I'm going to go through. If I see it's a second order differential equation, if I want to go and check to see if a function is a solution, I need to find the first and second derivative, and then I'll plug all of that information into the differential equation and then simplify. And if I get a true statement, then I know that it is a solution to that differential equation. And the last one we have is what's called an initial condition. Initial condition is additional information. You're going to be given a differential equation, at times, at least in this section, you're going to be given a solution, a possible solution. And you're going to have to verify that as a possible solution, that it is actually a solution. And then you can use the initial condition to fill in all the missing constants. So you're going to see when you look at a general solution to a differential equation, you're going to see a lot of C's. And it might be with C subscript, so C1, C2, and so forth. You're going to be able to use the initial condition to replace those values of C, or replace those C's with actual numerical values. First thing we're going to do is be able to verify a solution to a differential equation. So what's going to happen on this one? They're going to give you a possible solution, which in this case, y equals C1 plus C2 ln of x. And we're going to go through and we want to go and verify or determine if this is actually a solution to our differential equation. And our differential equation in this case is x times y double prime plus y prime equals 0. So we need to identify the first and second derivatives of y and plug that into the function. So the first thing I'll do is find y prime. So y prime in this case is going to be the derivative of this. Well, the derivative of C1 is 0. And then the derivative of C2 times the natural log of x is just going to be C2 over x. My second derivative is going to be negative C 2, c sub 2, over x squared. So now to verify that this actually is a solution to the differential equation, what I'm going to do is I'm going to take that equation, my differential equation, x y double prime plus y prime, and I know because of this I'm going to replace y prime with c2 over x and y double prime with negative c2 over x squared, and so I will get x times the negative c2 over x squared plus y prime, which is c2 over x. And now it's just a matter of simplifying. Well, when I go through and simplify this, the first part, x times the negative c2 over x squared, one of the x's in the denominator, the x here is going to go and get rid of one of the x's there. And so I'll get negative c2 over x plus c2 over x, which does equal 0. So therefore, I do know that this right there is a solution to this differential equation. Now that we know that it was a solution, that we had that c1 plus c2 ln x is a solution to that differential equation, now we can find a particular solution. And with this particular solution, I'm going to be told in this case, two pieces of information. First up, that I know that when x is 2, y is going to be 0, and y prime is going to be 1/2. So, in this problem, what I have to do, I'm going to first rewrite my differential equation, which is y equals c1 plus c2 ln x. And remember that y prime in this case was equal to c2 over x. And now the first thing I know is that y prime is equal to 1/2 when x is 2. So I know that 1/2 will equal c2 over 2. And from this, I can see that c2 is equal to 1. So there's my first constant. So right now, what I know from that is that my differential equation, my particular solution, is going to be, right now, c1 plus 1 times the natural log of x. Next, I'm going to go through and use that second condition. I know that when x is 2, y is 0. So when I do that, I'll put 0 in for y equals c1 plus 1 times the natural log. That's just going to be the natural log of 2. And then solving for c1, I get that c1 is equal to negative ln 2. And so for this, in this case, my particular solution to my differential equation is y equals negative natural log of 2 plus the natural log of x. That would be the particular solution based on those initial conditions that we had. Another thing you're going to be asked to work on is what's called a slope field. Now in a slope field, what you're going to be told to do is you're going to be given a differential equation. In this case, my differential equation is dy dx equals 1 plus y over x. And what happens on this is we're going to calculate various slopes, and then we're going to plot what you have is a line segment that would have those slopes. For example, I know, let's take a look, I have a graph here with 8 dots labeled. And we're going to go and identify the slopes on each one of those dots. So what you might want to do right now is pause the video and copy down this graph. So now to create the slope field, now you have the graph there, we'll create the slope field. What I'm going to do is I'm going to identify a point. So in this case, we'll start out with this point right here, negative 2, 0. So at negative 2, 0, at that point, x is negative 2, y is 0. So I'm going to plug that point in here. Well, when x is negative 2 and y is 0, 1 plus y over x is going to be a negative 1/2. And so what I'm going to do is I'm going to draw a line segment that goes through this point here and has a slope of negative 1/2. So what I'm going to do with that, I have that point there. I know it's going to be negative 1/2. So one of the things you can do is kind of think about where that line has to point, that the slope is going to point to. So if I'm going to go, it's going to be down 1 and over 2. It's got to point to this, to the y equals negative 1 right here. So what I'm going to do is draw a line segment there that goes through that point, negative 2, 0, and points there. And it's just going to be a short one. I'm going to take that, and it's going to go something close to that. And there we go. That would be that first slope. The next one we'll go with is the point right here, negative 1, 1. At that point, it's going to be at negative 1, 1. I plug that in here. I am going to get negative 2. So that means it's got to go from here, from that point there, it's going to go down 2 and over 1. So it's going to point to the same spot that we pointed to earlier. So in this case, I will draw a line segment there that points down. Going to try to make this go through that point. We know it's going to be at slope of negative 2. And so I'm going to go and draw my line through that point, pointing down there. Now what I'd like you to do at this point is to pause the video, and I would like you to go and make slopes, calculate slopes for each of the other points that you see on this graph. So you want to do one for the point at negative 1, 0, negative 1, negative 1, 1, 1, 1, 0, 1, negative 1, and 2, 0. So pause the video, put those slopes on there, and when you come back, we'll take a look at we'll compare your results with what I have. Welcome back. Once I've completed my slope field, this is what I came up with. In terms of this, and when you look at this, this is a problem. This actually is a problem that did appear on one of the AP exams, I think somewhere around 2007. But one of the things I want you to notice with this, when they go through and look at a slope field, if they ask you to do a free response where they're looking at a slope field, they're going to ask that you have some basics correct. Okay, so for example, when I look at these, they're going to look and see, are the slopes showing that the slope field is a slope field showing that the slopes are negative when they're negative? Are they showing positive when they're positive and 0 when they're 0? So in this case right there, here, here, and here, we have negative slopes. Here, here, and here, we have positive slopes. Now, they will not necessarily spend the time to make sure to go through and make sure that there is a difference, that there's a difference here between these, that they are actually, that this slope really does have a slope of 2, that has a slope of 1, and that has a slope of 1/2. They're going to look at that and say if it's relatively close. Now, generally, on a slope field problem, if they have one on the AP exam, making the slope field will just be a couple points. It's the stuff you do after that that will come into play and be worth more on the free response problem. But at this point, I just want you to be able to look at a slope field and be able to determine what it is and how it was created. The next thing we're going to be looking at is once you have a slope field, or and a lot of times they'll give you a slope field, how do you go through and determine how to draw this particular solution? Well, what you're going to do in this case, they're going to give you an initial condition. So on the first one I'm going to do is 4, 0. So that gives me the point right here. 4, 0 is right there. And so what I'm going to do from that point, I'm at right there, I'm going to use my slopes to help me approximate what this curve should be doing. Okay? Now, please keep in mind, it is an approximation. It's an approximation. It should be somewhat close, but we're not looking at something that's going to be super accurate. It's going to be very close though. For example, you just want to make sure that you're following those slopes around. Like at this, if I was right up here, I would expect to be going in this direction. I would not expect to see something like this. Okay, so as you're working on these things, as you draw, we start at this point, and I'm going to use the slopes to kind of give me directions around. You can kind of see I come through, I get to the point where it's level, and then it will continue on, and it will get steeper, and we get to here. Okay, and we can keep going, keep working our way around. And eventually we get back over here. Now sometimes you'll meet up, sometimes you won't. Now I'm probably a little bit off. In this case, I'm a little bit off over here. It probably should have come out more like this, but you get the idea. Another one we have is at the point -2, 1. So -2, 1 puts me starting right here. And so it's going to come down and then go like this. Again, try to match up the slopes as much as possible as you work your way around. I go through and eventually get back over there. And again, I'm probably off a little bit over in this area, but you try to be as accurate as you possibly can. Last thing we need to look at is Euler's method. Now, Euler's method is a process that will allow us to generate points on an approximate solution of this differential equation. Now, things that you're going to need here is you're going to need to know the differential equation. You need to know an initial condition, and you have to be able to identify dx. Now remember, dx, that is the same thing. That's equal to delta x. So you're looking at what really is the change in x. And what we're going to do is we're going to go and calculate what dy is. Okay, and we're going to use that dy, remember, in terms of the differentials, that is an approximation of the actual change in y for that equation. We're going to use dy to give us our next y coordinate. For example, in this case, on this problem here, I noticed that my initial condition is 1, when x is 1, y is 2. It's already given to us in the table. And I know dy dx is x plus y. And so what I can do is I can calculate dy dx. I know dy dx is just going to be x plus y, so in this case, dy dx is going to be 3. Now what I have to do is figure out what dy is. Well, dy is going to be what I get when I take dy dx and multiply it by delta x. So in this case, I look at this problem here, and I notice that my x values are going up by 1/2. So what I'm going to do, every time I find dy dx, I'm going to multiply that by 1/2, and that will give me the dy. So in this case, when I multiply 3 by 1/2, I will get 1.5. So I can now use that 1.5 to calculate my next y coordinate. This is saying that when I go by dy, when I go up by 1/2, my change in y is going to be real close to 1.5. And so in this case, I started at 2, and so I'm going to go up 1.5. So I take 2 plus 1.5, and 2 plus 1.5 is going to be 3.5. At this point, we start this process all over again. I know dy dx is x plus y. So if I take 1.5 plus 3.5, I'm going to get 5. So I know dy dx is 5. And again, since delta x is 1/2, I know dy is going to be 2.5. And now to calculate the y coordinate at 2, I'm going to take the 3.5 and add the 2.5, and when I do that, I'm going to get 6. And I can continue this process as I move forward to go and generate more and more points, so to give me another approximation of that differential equation. Notice this one is a little bit more, gives you a little bit more better idea in terms of the location than the slope field. Slope field, you kind of just approximate it as you draw it. You come close. This one is actually going to give you some points that are fairly accurate, but they're not going to be exact. So now let's take a look at another one here. We have dy dx is equal to negative x over 2y. And that this one actually is that slope field that we saw earlier that I drew. And you'll notice my initial condition is negative 2, 1. And so what we want to do here is we're going to go and generate some points. And I'm going to ask you to go and find the values of the y coordinates at each one of these locations here in the x. So to start out with, dy dx, I know is opposite of x over 2y. So when I plug in a negative 2 and 1 in for x and y, I will get that the slope here is a positive 1. And so we're going by 1/2. And so dy is going to be about 0.5. 1 times 1/2 is going to be about 0.5. And so that means my y coordinate here, I would take 1 plus the 0.5, I get 1.5. What I would like you to do now is I would like you to go and generate the remaining points here. Now you might want to have your calculator, but use your calculator when necessary and give me decimal points. If you need to round it to about 3 decimal places as you progress. So once you get that done, come back to the video and we'll take a look at how your results compared to mine. Okay, welcome back. At this point, I hope you should have all completed the slope field and gotten these points. We did as we went through and did this. What happened on here is that eventually we get to a point where we don't get a fraction. Like here we had delta dy was 0.5. Here we had that it was 0.25, and we can deal with those. Those are easy. But then right here we got a decimal that would extend very far, and it actually came out to be 2/7 if you were to go through and do it by hand. But the decimal, we would just round it to 0.286. And so therefore dy was 1/7, which would be approximately 0.143. And when I take 1.75 plus the 1.43, I would get 1.893. And then plugging everything in. At this point, I wouldn't even bother working with the fractions anymore. And again, we're approximating, we round it to 3 decimal places. So I got 1.132. Half of that would be 0.066, and I would get 1.959. And again, when I found the 1.132, I used the negative 0.5 for x, and I used this value here, 1.893, the rounded version for y. So if you actually use more decimal points, you might have a more exact answer than I do. So with that, this will conclude this video. We will look a little bit more. There's a couple of problems that we'll do for examples as well in terms of the types of problems that you're going to have to do in terms of identifying a solution when I give you a differential equation. Example, how to go through and solve something like this. But with this, I hope you are enjoying you enjoyed your weekend, or that you enjoy the long weekend, and we'll see you in class in our next class.